Like Erica, like you mentioned, I'm just basically filling in for Paramesh, who was the research tech that was in this project. I want to explain to everyone how we came about this very insightful picture and the research that goes behind this. I want to start off about just explaining how we came about what we're doing. My background is as a cardiologist, an academic cardiologist. My medical background is on electrophysiology, as sort of a day job where we're putting pacemakers, defibrillators in. And my PhD was on looking at materials, in particular materials related to energy harvesting. And I worked on stem cells in particular, induced pluripotent stem cells, which are stem cells from us as humans and which can be differentiated to become other types of cells. And in my case, heart cells. And I'm here at the Lange Lab at the Koch, which is a tremendous environment where we have a lot of interdisciplinary work and a lot of interdisciplinary work that actually has impact in the clinic. And we're sort of playing around with a lot of the sort of material science, polymer science, and implications of that. And one of the points that got my interest was, how do we look at harvesting of energy in a safe, sustainable, and efficient way? And a lot has been done in this field, but very much in the way of research, but very few in the way of accessibility. And how can we really push that boundary for medical use, and in particular clinical use in general? And one of the points that I was interested in was sort of this concept of batteries. So we're all afraid what batteries do, and we know what batteries are accessible. But with our current point and with the environmental issues related with batteries, we wanted a safe and renewable source of batteries. And one of the points that I was keen to involve was the application of cellular components. And what I meant by that is, given our interest and given my background in stem cells, can we use stem cells, and can we use our sort of kinetic power in beating heart muscle, heart cells, to initiate that process of external battery use and harvesting that. And we sort of played around technically, and very happy to announce that we've sort of moved on from how we extract these cells. We have a very unique system of doing that. We extract cells from urine, normal urine, and we engineer those cells to become the very stem cells, the induced pluripotent stem cells, and which are then differentiated. That means we are putting chemically defined components to shift the whole reprogramming of that cell, of that stem cell, to become a beating heart cell. And we're talking about doing that in a larger scale, and that's what we've sort of been working on, and we've sort of optimized that, so we're getting lots and lots of these beating heart cells, and you can see that as a little raft of beating cells, similar to what happens in the heart. And then so that movement, that sort of natural kinetic movement of beating heart cells lends itself to a very interesting source of power, of kinetic power. And the key differential here was, how do we take that kinetic power, which is really just similar to what you and I are doing now when our hearts are beating? How do we try and see, can we access some of that? Can we even harvest some of that energy? And can we harvest that energy to an order of magnitude above what's currently possible? And we were looking at different materials. One of the materials that we are particularly interested in is zinc oxide. And zinc oxide has been used previously because it's a very conductive, cheap material to use, but it's one of its key characteristics is that it has this ability of being able to develop a charge when you push on it, when you mechanically deform it. And that's called piezoelectric characteristics. And what that allows the zinc oxide to do is take that sort of change in deflection or of movement and take that kinetic mechanical energy and convert that to the energy that we want to do, which is essentially to store that for battery use. And our thought was, can we produce this zinc oxide, but at a much, much smaller scale, in particular in the nanoscale? And to give you a context of that, we're talking nanoscale is 1/billionth of a meter. So we're in the sort of ranges of below and sort of in that realm of DNA. And we wanted to go to that lower levels because you say, if you have at such a small scale, if you had almost little minute nanoscale farms of this, can we sort of use that as a means to upscale the whole process of harvesting? And so it led us down this track of active research that we're still working on. And so this is how this was all born about, that we wanted to understand the properties and behaviors of these zinc oxide. And if we were to miniaturize it, what are the implications of that? And from my particular sentiment, I was very interested because obviously this has implications for biosensors. The way we currently put defibrillators, pacemakers always require an external source of energy. Could this be something to look at? And what we really wanted to do is, how do we know that we're producing the zinc oxide? This is obviously a chemical process that we were developing. And this is where Paramesh was a real project that I was sort of guiding him towards, to say, look, we're now trying to make homogeneous zinc oxide, and we want it to be as a layer. So can we get these almost hairs of zinc oxide to see if we can deflect that? And so to characterize that, because it's in that nanoscale, we used the sort of SEM images, as you'll see, and it's a very easy way, but also a definable and objective way to characterize the properties that we need. So it was a very easy way to say, yes, has the chemistry worked, or no, it hasn't. And then I wanted to share with you where this whole stem of the discussion came from. Why did we pick the term as it is? And I just want to spend a bit of time on that. It's an interesting story. So Jules Verne, a French author, was writing a lot on science fiction. And one of the major books back in 1869 was 20,000 Leagues Under the Seas. And the French title you have there, the 20,000 Lieues sous la mer, Tout le monde sous-marine, is really the world tour of underwater. And what he described is very interesting, of this submarine-like machine called the Nautilus, which was discovered by people who had left New York, and they thought they were seeing a sea monster, and it actually turned out to be this Nautilus. And what the Nautilus was doing, it was going around the Pacific Ocean and seeing different oceans and traveling across the floor bed of the oceans, and it would created a whole new world for people to view. Now, the book, obviously, 100 years before of the whole instigation of submarines, was a very insightful view of where we are today. But there's a very interesting point which we wanted to capture in that whole book, which I think says a lot about why we chose that title. And that is, the whole option there is, the book 20,000 Leagues Under the Seas talks about where humanity and sort of the whole notion of trying to live for a better humanity using science, using sort of less pollutable forms of understanding, and using science to actually see. And that was a very interesting point that came out from this discussion. So when we were looking at the zinc oxide, that's one of the things that really comes out, that we are using science at this nanoscale, and getting information was something that just really stood out from us. And then when we first started, I'll draw your attention to this picture on the left of orange. This is what we initially got. And these are what I would call the weeds of this garden of zinc oxide that we're trying to get. And yes, they look pretty, but it's not actually what I wanted. I was, when we first did this, and Paramesh showed me this, I was like, okay, but that's not what we want. What we really want is the diagram on, and the picture on the right, where you see in green these sort of spikes of zinc oxide. These are sort of whole trails that we wanted to see, and you see it within this jungle. The perspective there is there's a jungle of zinc oxide which are in sort of this structures, towers in the nanoscale, and we, in the intermediary of trying to aim for that homogeneous garden, this picture that was selected by the judging panel came up. And again, we were sort of transitioning from different types of chemical processes to get to the end of this homogeneous garden, and then coming from total weeds or these sort of little plants of the zinc oxide which hadn't formed properly, we got to an intermediary. And that sort of came out that when you look at this picture, you focus on the fact that actually, oh, it's the center point that we were trying to actually discover, or actually trying to find. But that's not the case. The case actually is, from a scientific perspective, it's the bits around it that we were trying to get to. And this was a distraction, but it shows, and what really stood out is that it's sometimes in science, to get to the end goal, we have to sort of take stock of why things are not happening appropriately and optimize. And this is a good example of that we're not fully there yet. And this picture was taken at that point where we hadn't optimized the whole process till we had found our optimum sort of set of conditions, which you saw in the previous diagram. And so that made us really came out to me that this was a very important point to make. And Paramesh really liked the sort of the title of it, and it sort of rang true that when you look at things at this scale and you see this, you know, the science that we're doing is very intricate, and sort of every little option of that comes through. And so that was one of our defining points. And the beauty of this sort of snowflake-like item in the middle is to sort of really show that sometimes when we're looking at things, the focal point may not be the major output that we're seeking. And so this is the goal, as I said, so trying to make more of these lawns of zinc oxides in a homogeneous way. We have done some testing and we're already getting some power output. And there's still a bit more to go to actually optimize that whole sort of efficiency, but it's really directed us attention in the way that we want to move for our end goals. So I want to thank everyone, especially Paramesh, who obviously he started med school, and so he couldn't be here. And David Mankus, Margaret, Abigail, who are all part of the sort of the Peterson Nanotech Materials core facility, and they were integral in the sort of taking the picture and sort of characterizing this whole process for us. So we're eternally grateful. Gio Traverso and Bob, obviously here at the Coke, as our mentors, and obviously everyone in the Koch Institute, which as an institute still continues to inspire and is a wonderful environment where we can sort of share and have this sort of interdisciplinary discussion. So I hope that that was, I want